This talk is on clickjacking. I'm Warren. This is a joint work with my collaborators at UC Berkeley, Dev, William, Reza, and Don. Clickjacking is a malicious technique of tricking a web user into clicking on something different from what the user perceives. Now, in a classic clickjacking attack, the attacker renders an iframe transparently over a web page so that when a user clicks on what he thinks is the web page behind the iframe, he's actually clicking on the iframe, and in a real attack, this iframe would be drawn at like 1% opacity or something like that, so that the user can't tell that he's actually instead liking something. Now, this very simple attack won't work under some current and proposed defenses against clickjacking. Under these defenses, the attacker can place the Facebook like button in a frame, but cannot control what the Facebook frame displays. And additionally, the like button must be fully visible for a noticeable amount of time on the page before it becomes interactive. Say around 500 milliseconds is the proposed time. So in this model, the attacker can draw over the red area, but he can't interfere with what this Facebook frame is drawing in that rectangle. So today I'll present 5 novel clickjacking attacks that bypass these current proposed defenses, and they have to do with attacking limitations on human perception. We'll go into these 5 attacks shortly, but I'd like to point out that 4 out of these 5 attacks are applicable to touch devices, so they're not all going to be things that play around with the mouse cursor. And we also do an evaluation with 568 users on Amazon's Mechanical Turk to test out these attacks on real people. So in these attacks, we'll make 2 assumptions. First of all, the sensitive button, in this case, we're going to use the like button in our demos. It's something that voluntarily wants to appear on other web pages in an iframe. And there are defenses such as the X-frame options header, which the server can send to tell the browser, never allow this content to be rendered in an iframe. And this is useful in defending against some of the attacks, including our demos. But in this case, we assume that the content, such as a Facebook like or a PayPal donate button, agrees to appear on other pages. And secondly, the attacker convinces the user to play a game on the attacker-controlled web page. And people interact with untrusted websites all the time, so I think that's a reasonable assumption. Our first attack is on destabilizing the user's perception of the pointer. In this game, we'll tell the player to click a link on the left of the screen here. Feel free to click here. But what we'll do is we'll draw a fake cursor and hide the real hardware pointer, and have the fake one follow the red path while the real hardware pointer follows the black path on this screen. So what's going to happen is the player will start moving the mouse toward the here button that he's trying to click. And then as he approaches, we'll have the fake pointer move to the left. As the user approaches the here button, the hardware cursor is going right, but our fake pointer will go left to confuse the user. And as he thinks he should be getting close to the button, he'll notice that he's gone off course, and then he'll move the cursor to the right suddenly to fix this. That places his cursor over the like button, so that when he clicks, he'll mistakenly click the like button. Now here's a animation of that. Oops. All right. So in our capture software, it draws a yellow circle around the actual cursor, so you'll notice that it's actually off from what the user sees. And you'll also notice that when the player mouses over the like button, the real hand cursor appears. All right, so that could be a problem. And that's because the attacker has no control over the Facebook iframe under this defense model. So what we do to prevent this from stopping the attack is that we use a lot of distracting images to sort of take the player's attention away from the fact that his cursor has just appeared over the like button. So this is what the attack actually looks like. All right. So in that video, we used an effect called crowding, which uses a lot of stimuli surrounding the target to make the real target, the actual hand appearing, far less visible. So even if the user was dedicating a little bit of peripheral attention over to the like button area, it would be much harder for him to see his real cursor appear. Another thing we could have done is use this effect called filtering, where if we had a moving background, say, behind the like button, that would draw the user's attention immediately when he visited the page. But the brain would soon tune that out as a source of unnecessary distraction, so that during the attack, he'll have tuned out the fact that his real cursor appeared. Our next attack is attacking peripheral vision. I'll start out with the video of this game. The player puts his mouse over this play button in the corner of the screen and then watches these blocks fall into the holes, and he has to click the left or right mouse button as they fall into the holes to get some points. So while playing this game, the player keeps his mouse in the bottom left corner of the screen while he's watching the top right of the screen. And while he's doing that, it's very hard for him to know what's happening in the bottom left. In fact, you may not have noticed that on this slide, the bottom left has already changed to a like button. So when we execute the attack, we'll switch in the like button, wait for a few moments for it to settle in under the required defense, and then after that, we'll send one of these left click blocks to have the player click on the like button. Our third attack exploits motor adaptation. So here's a video of the game. It's a pretty simple game where the player has to click on these asteroids that appear and then click on a mineral that comes out to score some points. So we present the player with an asteroid at a random location, and when the asteroid gets clicked on by the player, it explodes and shoots out a mineral to a constant displacement directly above the asteroid, and it always moves to the same place relative to the asteroid. And the player gets used to this action of clicking on the asteroid, moving the mouse up, and then clicking on the mineral really quickly. So once we train the user to do this, we move the asteroid directly under a like button so that if he clicks the asteroid and then moves his mouse up the same amount as he's been used to, and then clicks again, he'll click on the like button. And it's really hard for him to avoid doing this once he's used to this click, move, click repetition. So there is a chance that he'll see the like button and then stop himself from clicking it. One thing we do to try to prevent this is that we have a lot of distracting objects in the game that sort of like buttons to sort of make it harder for the player to tell that that a like button has appeared. And we do this with several of our attacks, but we won't show the actual cluttered view in order to keep these videos simple. So here's what the game actually looks like. There's a lot of these gray rectangles and blinking lights to make it hard to tell when a like button has actually appeared. All right. Fourth attack is fast motion mislocalization. I'll show you the video of this. This is the simplified version without the blinking lights. So this time, they don't have to click on the asteroid, and a mineral comes out automatically in a random direction, and the player has to click on that to get some points. So this arrow spins around, picks a direction, and then a mineral comes out, and the player has to click on it at the end of its trajectory. But what happens in practice is that the player clicks a little bit beyond the mineral. And this is caused by an illusion known as the flash lag effect, where for a moving object at any moment, the brain perceives its location to be actually a little bit ahead of where it is. The brain does this to predict its future displacement, given its momentum. And since the player clicks a little bit beyond the mineral, we actually do award them points still so that they don't notice that they're doing this. And then when we execute the attack, we shoot the mineral toward a like button, and when they click a little bit past it, they'll click on the like button. All right, final, this one is on visual cues and click timing. Another pretty simple game. I'll show you the video. This asteroid is moving around along some path, and it flashes red periodically. And so the player has to click on the asteroid to get points, but only when it flashes red. If they click on it while it's still gray, we'll actually remove some points. Now, during the attack, we'll move the asteroid under a like button and flash it red, which prompts the user to click. And it'll get them to click on the like button sometimes. So when the asteroid passes under a like button and flashes, this causes a race model in their head. There's a go signal from the red flash and sort of a stop signal from seeing the like button telling them, no, don't click. So as an attacker, what we wanted to do was first slow down the stop signal. And again, we do this by adding a lot of distracting images, so it makes it harder for the player to notice the like button. And that slows down the signal of this seeing the like button, telling them not to click. We also want to speed up the go signal. And we do this by awarding more points based on how close to the red flash they click, so that they're really itching to click when it turns red. All right, now on to our evaluation. We had our participants on Mechanical Turk try out one game and then answer a survey based on the 2012 clickjacking work by Huang et al. To determine whether or not we actually attacked them with these clickjacking attacks. And the survey goes a little bit like this. So first we ask whether the user thinks he saw a like button. And if he did, the survey asks if he clicked on it and whether that was intentional. And if the player say they didn't saw the like button, it just asks if they would approve if they saw this game on their newsfeed. So if they did intentionally click on it, or either that or they approved that it would appear on their newsfeed, then we didn't count this as an attempted attack since they legitimately would have liked the game. It's when they either disapproved or didn't say that they intentionally clicked on it that we counted this as an attack, and we measured the success rate on these. So for those users, we checked whether the game ended by the player clicking on the like button or just the game ending normally, which takes around 2 minutes. Oops. All right. So we had about 150 users for each attack, and despite our best instructions, some of them did try more than one of our games, so we removed those in order to have only the first-time participants. That's the number you see in the subjects column here. The attacked column shows how many of the players did not legitimately like the game. And finally, on the success column, those were, of the attacked players, how many fell for the like button. So these demos were pretty powerful, ranging from 20% to 99% success rates. But one thing to note is that they are just a lower bound, and a really determined attacker might be able to do better by doing some of these following things. First, they could build a game that adapts to the player based on their performance. Second, maybe use a better model of their pointer movement and predicting their clicks. And third, since each of these demos really was intended to demonstrate a single limitation of human perception, an attacker would probably try to use more than one of these tricks to make a combined attack. Finally, we assumed a pretty strong defense in ensuring that the like button was visible for an entire second, up to 3 seconds sometimes. But if this defense were to be deployed, it's not deployed right now, but if it were, it would probably require not so long of a delay in order to keep the usability acceptable. And there are many other attacks that are possible, and human perception is a vast and well-studied topic. So one example is change blindness, where these test subjects failed to see a change in an image looking directly at it. So maybe an attacker can switch in a like button while the user is actually looking and not have the victim notice. This invisible gorilla video is a really classic experiment where a user fails to notice like a dancing gorilla in the middle of the screen. So that might be a little harder to conceal than a like button. So in conclusion, secure UI design really needs to take into account these limitations of human perception. It's sort of weird to see that they're relying on these simple heuristics of like the button needs to be visible for, say, 500 milliseconds. We may need to change the defense specification, or at least disclaim that this won't solve absolutely everything. And yeah, so designing a secure interaction mechanism that takes these human limitations into account is just critical for security. Thank you. And I should add, if you want to try out some of these demos, they're available online at this URL. Yeah. All right.
Hi, I'm Luke Desdetels from North Carolina State University. I have a question. If you can go back to around slide 36, it's when you were deciding which ones counted as attacks or not.
All right.
Maybe it's that one or maybe something else.
Or do you mean this one?
That one, yeah, the flowchart.
Right.
I don't understand how you determine that if they accidentally click it and they didn't intend to, that it would still not be an attack just because they're okay with the game. It seems like what you're trying to evaluate is how effective are these tricks, and you want to know if they were stealthy or if they were detected. But it seems like it would be less effective if you, well, less accurate if you throw out these results.
So we threw out the results where the player self-reported that they clicked the like button. So
no, the game on newsfeed, do you approve of it showing there even if you didn't see the like button?
Oh, I see. Right, so the cases where they didn't realize they clicked the button and they did, but they said that they would approve. Right. Yeah, so that is one thing we could have done. In this case, we just wanted to have sort of the end-to-end, whether it appears on your news feed or not, as the determining factor of whether you were tricked or not. But yeah.